All right, Biology 11. Our next topic in our evolution unit is cumulative selection. So let's get right into it. There is no note currently for this on your D2L page, so it's a short topic. I usually write this on the board, so I'll kind of do my best to give you the same presentation here in this video. All right, so cumulative selection. What cumulative selection is, it's a process in which small changes accumulate over time because of their selective advantage. Now we know selection is that pressure that all living things feel on them. It's the grind that Mother Nature puts on you. It says, hey, can you do this? Can you do that? Can you do that? Right? Her checklist. And so cumulative selection is the acquisition or acquiring or gathering of small little beneficial changes over a long period of time. Right? And because they are beneficial little mutations and changes, they gather and eventually form a very complex trait. So we usually use cumulative selection to explain complex traits. Right? Now a complex trait, a great example of one, is the eye. Right? The eye is a very complex trait. It has many different parts to it. It has the, if you think of our eye, it has the rods and cones, the specialized cells in the back of the retina. You have the optic nerve, the vitreous humor, the cornea, the aqueous humor, the iris, right? The lens. So there's a whole lot of stuff that goes into this eye. It's not just one piece, right? So it's pretty complex. The ear is another one, right? Our ear has many different parts. There's a hammer, anvil, stirrup, tympanic membrane, auditory nerve, right? The cochlea, it's all in there. So that's what we're talking about. People argued against Darwin and said, how can a mutation result in an eye that has all of these, interwoven parts that work together so perfectly, right? Only a God, a creator, could put together something like that. So this is one of the stumbling blocks at first that people that held people back from believing in evolution by natural selection. But Darwin did have a way of explaining these God-given traits, and it was through cumulative selection. So I'm going to go over an example with you, and I've drawn some diagrams here of how our eye, we'll do the eye as our example here. All right. If you remember in Darwin's dangerous idea, right? In Darwin's dangerous idea, there was a biologist, right, an anatomist that recreated the eye. So if you go to that film, right, the YouTube video, and that is covered at the 1 hour, 2 minute mark, to the 1 hour and 11 minute mark. If you rewatch that, that's cumulative selection. And he's recreating the eye in very much the same way I'm going to describe it to you now. All right? So, Darwin's dangerous idea, this little 9-minute section, we'll go over both of these ideas. The eye is the example of cumulative selection. So, let's go over this using the eye as our example. All right, so the eye, it's theorized, may have started out as just some photoreceptive pigment-filled cells and some nerve cells. So we've got the orange cells here are your photoreceptive cells, your pigment cells, and then you've got the blue ones, which are your nerve cells, which are attached to the nerve fibers. The black cells here are epithelial cells. Epithelial cells are like what's on your skin, right? So these are specialized cells that are not like the coating of your skin, all right? These cells would only be able to detect light, right? It'd be like when you have your eyes closed and someone flicks on or off the lights in the room. You can tell, you can't see anything about you, but you can see when it's darker, where it's lighter. Or if one half of the room was lit and the other one wasn't, you'd still be able to close your eyes and go, okay, that side of the room, that's the lit side. This side over here is the dark side. So that would be the first thing. Then some small changes, right? the accumulation of small beneficial changes. So here we see, after a couple of changes have been made, the eye is now indented, and we have what's called the cup eye. So we still have our cells, right? The pigment cells and the nerve cells, same colors, and we still have the epithelial cells, but this indentation would allow for some shade, right? And this protects those specialized cells, right? If you think about it, when it's really, really bright out and your eyes have no protection like here, it hurts your eyes and your visual acuity isn't very sharp. So what do? Well, you put on sunglasses and cover your eyes, or you put your hand over your eyes or put on a hat, and that shade created by the hat or putting your hand over, your eyebrows, that allows you to see better. It cuts down on the amount of light getting in there and basically burning up these cells. So that's what this indentation would do. It would help protect these cells and add to visual acuity. Another few adaptations would occur, and what we would see is the indentation going even further, and then it's starting to close over in the front. And this is called the simple optic cup eye, or what many biologists kind of give the nickname, the pinhole eye. In elementary school, you may have made pinhole cameras, and you look and you put the little pinhole usually in the Smarties box, I believe, and you can see images really well, and kind of like, wow, well, that's what this is. So here we can see what changes have been made. Well, the indentation has gone further because it was beneficial, it was good. We've got more pigment cells and nerve cells in there. This is the beginning of a retina. And then we've got the nerve fibers coming together to form an early optic nerve. All right? So a few things have changed or have modified a little bit further. And why have they changed or modified it and now stuck within us, within the creatures? Because they're beneficial, right? Good mutations tend to stick around. Important to notice that there's an exchange here between, and these are mainly marine creatures, there's an exchange between the external environment and the internal area of the eye here still. So this water that's out here would still be the same water that's in that cavity. Excuse me. A few more adaptations occur, and we can see now more pigment cells, more nerve cells. The optic nerve has grown in size. The retina has grown in size. And now we've got a covering, but it's very, very thin. Epithelial cells are very, very thin, right? One layer of our skin is next to nothing. It's so thin. You can see through it pretty much. So light can still get in, and now we've got the formation of a crude refractive lens. All right? So the lens is key because it allows us to focus light onto the retina and carry the information from the optic nerve to the brain. So the formation of this coating in front, which still allows light to come through, and the lens are benefits. So it's kept and it's passed on to future generations. Some more mutations occur over a long period of time. Again, this isn't like in 10 years this didn't happen. This took place over hundreds of thousands of years. And then we have the complex eye. And this eye is very much like ours. All right? So if you look here, we have our lens, right? The pupil, the black part of our eye, would be right here where the light comes in. So the light would come in this direction, pass through this. We have the iris, which is the colored part of your eye. So if you have brown eyes or blue eyes or green eyes, that's the iris. We have thin muscles that are in here now that can move the iris. And basically what the iris does is it dilates or constricts in response to the amount of light around the eye, right? So when it's really bright, this will close up a bit. If it's really dark, this will open up a bit and allow more light into the retina. So things like that. The inside of the eye now is sealed off. We have the vitreous body in here, which is a fluid in the back of the eye. The retina that we have with rods and cones and nerve cells that lead back to a highly complex, larger optic nerve. All right. In front of the eye, we've got the protective cornea now, which would have resulted from these, modifying over time, these epithelial cells here. And we've got a fluid in here to bathe these parts. All right? So there's no longer the exchange of fluid, like here where you had fluid from the outside could easily get to the inside. Here, the eye has its own fluid. So this is the exact same example that was gone over in Darwin's Dangerous Idea by the anatomist when he reconstructed the eye step by step. And that's what cumulative selection would be. A series of small, beneficial changes that would have gathered over time. If it's good, you keep it. If it's bad, you probably end up dying. As our eye evolves, it helps us out tremendously. All right? And there are creatures today that still have all of these eyes. Right? You're thinking, why wouldn't everything have this? Well, because some creatures can survive just fine with these. Right? So, for example, there are creatures called limpets. And most of these will be marine creatures. There are creatures called limpets that have basically a pigment spot. And it serves them just fine. Right? Then for the pigment cup eye, there's slit-shelled mollusks. Right? Slit-shelled mollusks. And they have this type of eye. Present day. They haven't evolved any further because they survive just fine with this pigment cup eye. Another marine predator is the nautilus, and this one is shown in Darwin's Dangerous Idea. The nautilus has a pinhole eye, right? And it hasn't gone any further because it works just fine with this. They're surviving no problem. And then we have a marine snail called the murex. It has this primitive eye with the primitive lens. And then, of course, if you look at me or you or your dog or a wolf or any complex animal or mammal, we have these eyes, the complex eye with the cornea and the lens and the muscles and the retina and the optic nerve, right? So that's cumulative selection, sort of step by step. I'm sure there were many more little changes in between there, but can't take all day to do it. So again, Darwin's Dangerous Idea had a review of this. The times were listed earlier. I'm going to move this. Now, I'll take pictures of those and put them onto the Edsby page as well. So our next idea, right? Now, that's Darwin's explanation. A series of beneficial small mutations that eventually lead over thousands and thousands of years to a very complex, organ, the eye or the ear. What people used to say, they had this watchmaker idea. They said, these very complex organs, like the eye, are very much like a watch, right? A watch has a series of cogs inside that all have to work in little, screws and levers and everything else, and have to work absolutely perfectly for it to keep time properly. And they said, just like you have the watchmaker that carefully crafts each little cog and screw and wheel inside of the watch, that's God. And God was the watchmaker for things like, well, as a watchmaker makes a watch, God would make things like our brain and all of its parts, our ear and all of its parts, and of course our example, the eye and all of that, right? All the parts that are involved there. So how do you get by this? Well, Darwin said basically we've got all these small beneficial changes. One of the best explanations of how we could still get there without having, God the watchmaker, was written in a book called, ironically, The Blind Watchmaker. Now, The Blind Watchmaker, it's actually a book, and it's written by, I believe, Richard Dawkins. And what he says is that when you have a complex trait, let's not just go to God right away. Let's figure out how, God gets this to work. And so his idea was not that there was a God doing this and I don't want to unmask anyone's faith here, but his idea was that all organisms have descended from common ancestors solely through unguided, unintelligent, purposeless material processes like natural selection, right? So again, the mutations that occur that change the traits of the eye over time, they're unguided. There's not a purpose to them. It's not like, oh, let's get a better eye. Let's randomly change that DNA and get a better eye. No, the DNA changes are random. We don't know what the effect of them is going to be until they occur. And then once the mutation has occurred, then the effects are known pretty quickly, whether it's good or bad, right? The watchmaker had intelligent design when he builds his watch to keep time. God has an intelligent design when God builds the eye. And he said, our eye is very complex, but these changes are not intelligent. They're unintelligent. They're random, right? They're random little changes in your DNA that could occur anywhere. So there's no, purpose or direction for this. But again, if that random change in your DNA helps you out a lot, then it's going to stick. It's going to, you're going to survive. You're going to mate and reproduce and pass on that change in your DNA. So the idea is, with the blind watchmaker, that mutation, which creates change in traits, right? And we know that because mutation affects your DNA. Mutation is random. All right? There's no direction to it. You're right? That's like me saying, I'd love to have wings. I hate traffic. I would never have to sit in traffic again. I could just fly home every day. Well, I can't do that. Mutation is random, but the effects of the mutation are not. So you can imagine if you were a grizzly bear, which is a large brown bear, or a black bear, which is a large black bear, in the woods, you'd be able to hide pretty good amongst the ground and the different colors of the woods. If there's a random mutation, right? A random mutation, and now you are an albino grizzly bear, or an albino black bear, which I guess would make you like a polar bear, you can imagine it wouldn't be some random effect. You'd see that bear and go, yeah, he's not going to do very well here, right? The deer and whatever he's going to eat are going to see him from miles away. He's not going to eat. He's going to starve. Vice versa, the same thing with a polar bear. Polar bears are ideal for the snow up in the polar regions, right up in the Arctic. If one of their cubs had a random mutation and had black or brown fur, you can imagine the seals in that up there would say like, oh my God, look at that guy. There's no way he's ever going to catch me. I can see him from 3 miles away, right? So the mutation occurring is random, but the effect of it is, it's not, right? The effect of that mutation is not. Mother Nature will tell you pretty quickly whether that's a check mark or an X, all right? Anyway, that's cumulative selection, series of small beneficial traits over a long period of time that produces a complex organ or part of the body. All right? So, hope you understood it. And if there's any questions, give me a shout in the comments section below this video, or reach out to me through Edsby if you're one of my students. Anyway, I'll talk to you soon. Bye-bye.